Ethers are a very unreactive functional group. They're very similar to alkanes in that respect. They tend to be stable to bases, nucleophiles, electrophiles, and even mild acids. However, if we treat them with strong acids such as HI and HBr, so generally we have to use an acid that also has a nucleophilic counter ion such as a halogen. And if we heat it up, we can cleave the ether in half and produce two products. Generally, we make an alcohol and an alkyl halide. This reaction is generally considered an SN2 reaction, and so the halogen usually adds to the least substituted carbon and then eliminates the rest of the molecules, so starting from the oxygen uh, into an alcohol, in this case, an phenol. Here is the mechanism. If we start off with an ether and we add acid, the first thing that happens is the oxygen is protonated by that hydrogen of the acid. That produces this intermediate. This turns an oxygen, which is not a great leaving group, or an OR group that is not a great leaving group, into a much better leaving group by protonating it. The next step involves the counter ion, the conjugate base of our acid, in this case iodine minus, attacking the less substituted carbon. So it goes after the CH2 rather than the CH here, which has a couple of methyl groups. So it goes after the CH2 and then eliminates, starting from the oxygen and everything else attached to it. This is essentially an SN2 reaction, so that is why the iodine prefers to attack the less substituted carbon. That produces isopropanol and iodoethane in this example. In most cases that we do an acid catalyzed cleavage, we usually will observe the halogen attacking the less substituted carbon through an SN2 reaction, as we just saw. However, if we have the opportunity to form a very stable carbocation, such as a tertiary carbon, which is attached to the oxygen, we sometimes observe an SN1 and an E1 reaction instead. Here's an example. We have tert-butyl propyl ether, and we're going to add HBr and heat the reaction. Generally, the first step will involve the oxygen attacking the hydrogen and be protonated. And then that creates the opportunity to form a carbocation since we have a tertiary carbon next door. So this bond here between the carbon and oxygen, the electrons on it move towards the oxygen. That leaves behind a carbocation, which gets attacked by the bromine to form the more substituted product here through an SN1 reaction. The byproduct will be this alcohol here, which contains the oxygen plus the hydrogen that came from the acid, and then the propyl group. In this question, we want to predict the product from the following reaction. Notice we have a primary or actually a methyl group, and then on the other side of the ether, we have a tertiary carbon. We're going to add HBr to make this reaction occur. In this example, we have a tertiary carbon plus it is a benzyl carbon. So notice it's on the benzylic position, one carbon removed from the benzene ring. Both of those characteristics make this carbon very likely to be eliminated as a carbocation when we add HBr. So by adding HBr, we eliminate this carbon as a carbocation, which then gets attacked by the bromine to form this product that you see here, the SN1 product. The rest of the molecule, which includes this oxygen, the methyl group, and the hydrogen that was picked up from HBr, will be eliminated as methanol. And then in addition to that, we might observe a small amount of E1 product, and that would be from a carbocation being placed here initially, and then one of the hydrogens on either this methyl group or this methyl group being removed to form a double bond, which you see here.